Right. This is a simple example of an argument. It is one of a set of very small, simple arguments called rules of inference, and they all have Latin names. This one is called modus ponens. So modus ponens is a very simple argument. It just says if P implies Q and P, then therefore Q. All right. If P implies Q is true and P is true, Q must be true in order for that to work out. I'm going to show you a proof of this, and for this proof, I'm actually going to prove it by rewriting it in the other formats. So I'm going to write P implies Q, that chunk, and P. So there's our two premises, premise 1, premise 2, all together. And then that implies Q. So I'm going to show you how to prove this just using propositional equivalences. So that is my starting statement. And then what I'm going to do is I'm going to rewrite this as an equivalent statement. And what I want to do is show that this is a tautology, right? So I'm going to try to prove this is a tautology. I think the first thing I'm going to do is go ahead and I'm going to apply let's see, I'm going to apply a conditional disjunction equivalence right here, just inside here to this part. This implication here. So this is going to become not P or Q. There we go. And P implies Q. So all I did was I changed that into not P or Q. Now what I want to do is go ahead and distribute. I have an or inside the parentheses here, and then I have an and P out here. I'm going to distribute the and P over this or. So I'm distributing and over or. So what I'm going to get is I'm going to get not P and P or Q and P. So that is still all what's inside my hypothesis here. That still all implies Q. All right, now I'm going to simplify what's inside here because not P and P is false, right? This is a contradiction inside here, not P and P. So that's false or Q and P. I'm actually going to rewrite that as P and Q. There we go. That's just the commutative law. Oh, I just realized I forgot to do anything here. I'm supposed to do conditional disjunction. And then this was distribute. I should be citing my rules here. And then this is a negation law. And I also use the commutative law right here, but I'm not going to cite that one. That I told you don't need to cite the commutative law because it's pretty second nature. And then next, we have false or something, right? So you may remember when you were combining false and true with other things using and or, you've got the identity laws and you've got the domination laws. Let me go ahead and pull up my reference sheet here just so you can see which ones I'm talking about. Identity or domination. If you have something or false, that is an identity law. So in this case, false or P and Q, that's an example of that identity law. Technically it's backwards, but again, commutative could flip it around for us. So we can apply the identity there and say that is just going to be P and Q, and then that implies Q. So that's by identity. Now, this might look familiar. P and Q implies Q. This is actually, you on your assessment actually prove this is equivalent to true, right? So actually I'm going to put a dot there because this portion of it here is an exercise that I've assigned you. So I've shown you how to manipulate it to this point, and then that you can show that's true on your own. And then that would then complete the proof that this is a tautology and therefore this is a valid argument. Okay, so I just want to pull up the reference sheet. On the second page of the reference sheet, we have the list of rules of inference right here. And the rules of inference all have these sort of abbreviations. So the way they're written out here is a little funny. Here's abbreviations we can use. I just made up these abbreviations so that you can reference them if you want to by these, or you can write them by name. Here are their Latin names. And then here are the premises. So from these premises, you can conclude whatever it says over here. So modus ponens is the very first one. It says from P implies Q and P, we can conclude Q. Modus tollens is interesting. It's basically just the same idea, except from P implies Q, if you know not Q, you can conclude not P. Think back to P implies Q, the not Q, the not P. You may remember we had this thing called the contrapositive equivalence right here. P implies Q is equivalent to not Q implies not P. So essentially, modus tollens is kind of like combining that contrapositive with modus ponens to make a conclusion. So it's pretty, it's just kind of like a spin on modus ponens. Hypothetical syllogism kind of makes sense. If P implies Q and Q in turn implies R, then P implies R. This is essentially saying that the implication as a logical operation is what's called transitive. It kind of carries through, like it carries through one element to the next, and then you can connect the beginning to the end of the chain. That's kind of what this is showing here. Disjunctive syllogism, if you know P or Q but not P, it's got to be Q, right? If it's got to be P or Q, but it's not one of them, it's got to be the other one, right? That's a disjunctive syllogism. And then the rest of the ones here, at least up until universal instantiation, are relatively straightforward. Resolution, I think, is the only one that is kind of tricky. But I'm gonna leave it to you all to sort of make sense of these on your own. So think about these, and I just want you to wrap your head around them and make sure you kind of feel comfortable with why these should be true. The last four down here are actually ones that we're going to use for dealing with predicate logic. So these are rules of inference for predicate logic. We're going to use those in a future video.